Okay, well, good morning, everyone, and thank you for your interest in this topic. As a passionate advocate for structural fire safety, I'm really honored and thrilled to be here today and have the opportunity to share with you my experiences with structural fire protection. But before I begin, I'd like to thank this Colorado chapter for organizing this webinar lecture. And I'd also like to kindly thank the contributors to the SEI Futures Fund for making this possible. So the webinar is going to be broken down into 4 parts. I'll start by briefly covering how we've traditionally protected structures from fire, as well as introduce the emerging performance-based method known as structural fire engineering. Then, supporting this movement, I'll cover recent efforts by ASCE to standardize the practice of structural fire engineering for the betterment of our structural engineering community. From there, I'll walk you through an example structural fire engineering design from beginning to end. So I really want to promote transparency. I don't want you to think about this as some type of black box. You probably know more about this subject than you may realize. And then lastly, we'll examine the industry impact that structural fire engineering, as it emerges and grows here, will likely to bring in the coming years. So with that, I'd like to jump into the first section, which gives a little bit of context to what I'm going to talk about. So, really big picture. Why do we thermally insulate structural systems? Structural fire protection addresses the low probability but potentially very high consequence event of an uncontrolled fire within the built environment. And under this rare condition, it's important that we protect lives as well as satisfy additional performance objectives that are important to society. Fire sprinkler systems are pretty ubiquitous in buildings, and there's no question that they raise the level of fire safety overall. However, we really need to appreciate that they have certain performance limitations, and I, as a fire protection engineer, as well as a structural engineer, I've had the opportunity to partake in the design of sprinkler systems. And they're not like how you see in the movies where they all go off. They're actually hydraulically only designed for a very small number or cluster of sprinkler heads to go off to control a single ordinary fire. So as the fire size increases, the reliability of the system decreases. So there could be cases, extraordinary events, where the sprinkler system is not effective at controlling the fire and it becomes uncontrolled. And this is where structural fire protection comes in. This is its real purpose. It serves as a critical backup safety system in those events. The traditional method of designing structural fire protection, which you've probably had some exposure to, is termed standard fire resistance design, or more commonly known as the prescriptive method. Within standard fire resistance design, qualification of fire resistance is based solely on standard furnace testing, as shown in these pictures. And within this context, fire resistance has a very specific meaning. It's the time that a mock-up assembly withstands furnace exposure during a furnace test in accordance with the furnace test specific acceptance criteria. It's important to be aware that furnace testing has remained relatively unchanged since 1918, so we've exceeded the century mark on this. And U.S. code requirements for fire resistance date back to the 1927 Uniform Building Code. The furnace test method essentially decomposes a structural system into individual components. These components are tested independently without any interconnectivity or interaction with each other, and structural connections are excluded. So, as a viewer of this, a structural engineer, you're probably scratching your head thinking, how do you get load to ground if you're just looking at things in isolation? And we'll get into that. Thing to be aware of is that the test assembly size, or the mock-up specimen, is governed by the dimensional limitations of a test furnace, which are typically 14 feet by 17 feet. So the longest span you can have in this test is 17 feet. As shown in this rather crude drawing that I did, the furnace test essentially represents a single intense heating exposure, shown in the dotted line, or the dashed line. Actual fires in buildings have a distinct growth phase and a decay phase as the fuel load. I'll refer to fuel load. Fuel load is basically combustibles, things that can, basically embryos of energy that can be liberated through chemical reaction to produce heat as an exothermic reaction. So as the fuel load is consumed, the duration of the fire comes to an end. So the duration is finite. It's not infinite like as implied by furnace testing. So furnace test exposure does not actually represent the fire dynamics of an actual fire. Before we jump into the technical aspects of structural fire engineering, it's very, very important that we understand this. This is absolutely fundamental. There is no correlation between performance in a furnace test that qualifies fire resistance per its acceptance criteria and performance of a structural system under in situ thermal conditions from uncontrolled fire. So this concept was not actually written on ancient scrolls centuries ago, as I imply here for effect. But as I mentioned, it's absolutely fundamental to the entire premise of standard fire resistance design and structural fire engineering. To highlight this, I show a hypothetical design example of two structural seal systems, and pardon my ability to draw. These are hand sketches I did, and they're highly exaggerated. I understand that the bottom one you're not going to see, but it's just to prove a point. But let's look at that second system. It obviously has a higher capacity to endure fire exposure, owing to the fact that it has a very short span and extremely robust connections. However, if 1 inch of fireproofing is applied per this specific UL listing or many other listings of the like, both assemblies would be qualified for the same level of fire resistance. Now, this may seem counterintuitive to you, thinking like a structural engineer, and this is because standard fire resistance design does not necessarily credit nor does it discount the capacity of the structure to endure the fire. Standard fire resistance design essentially prescribes insulation with the intent of limiting the heating of individual components in order to have a mitigation of the risk, but not a qualification of the risk. Accordingly, the vulnerability of buildings to structural failure due to uncontrolled fire presumably varies across different jurisdictions which have differing structural design requirements for ambient loads such as wind and seismic. And also, just as a function of the building system that you select or the component configuration. So coincidental ambient load considerations that you make for your structure, you may unknowingly be affecting the intrinsic fire safety of the structure, irrespective of the fire resistance that is qualified. Also, restraint conditions differ extraordinarily between a furnace test and actual construction. This is important because restraint conditions may dominate the behavior of a structural system under fire, even more so than the temperature of the members and the loss of strength and stiffness of the material. In a furnace test, a steel beam and concrete slab would be restrained equally at each end. In actual building construction, the beam and slab usually have varying conditions of restraint. Also, the restraint provided by a furnace bunker is an order of magnitude stiffer than actual building construction. As a performance-based alternative to standard fire-resistant design, structural fire engineering aims to control the heating of the structure intelligently, as well as provide adequate structural endurance to satisfy explicit performance objectives. And within this framework, thermally induced forces and degraded material properties due to fire exposure can be limited by the rational and intelligent allocation of structural insulation, control of fuel loads, or other fire exposure mitigation techniques that are passive. So we can't rely on sprinklers, which I'll get to. Also, the ability of a structural system to endure fire effects can be enhanced with specific member sizing, connection and reinforcement detailing, or other means to provide added structural robustness. So how is structural fire engineering different from standard fire resistance design? To start, let's examine these approaches in the fundamental design philosophy that we all appreciate in structural engineering, in which the capacity, both globally and locally, must exceed the demand implied or applied. As we discussed, standard fire resistant design is based on an empirical indexing system which excludes consideration of realistic thermal demands and structural system response. To a certain extent, standard fire-resistant design measures the structure's heating using standard furnace testing, but it does not account for the capacity of the structure itself to endure fire exposure, nor does it properly evaluate all aspects of demand, most notably the very important thermally induced forces and their consequence on connections. As an alternative, structural fire engineering explicitly evaluates all aspects of demand and capacity in a similar manner as other design loads are treated in structural engineering practice. In recent years, there's been a pretty significant push to establish structural fire engineering as a legitimate practice in the United States. Conveniently, this effort falls within an even bigger movement that's been mentioned in the announcements, and everyone, I'm sure, has had some exposure to in structural engineering in our community. Specifically, the push for structural fire engineering aligns with ASCE's high-level goals for enhanced building resiliency through advanced structural design, as well as the advancement of performance-based design overall. Also, NIST has long advocated for a regulated performance-based method, as shown here in Recommendation 9 within their 9/11 investigative report of the World Trade Centers. Specifically, it states that NIST recommends for the development of performance-based standards and code provisions as an alternative to current prescriptive design methods. Also, NIST identifies ASCE 7 as a logical place for provisions for a performance-based method. So that concludes the background and context to which I'm going to discuss. Now I'm going to go a little deeper and talk about recent industry standards that are supporting this movement. So as you're all aware, ASCE 7 serves as the parent standard for structural engineering in the IBC. And I'm sure you're aware it's on a 6-year revision cycle, and we're gearing up for the 2022 edition of ASCE 7. The current edition, if you're not aware, has a new Chapter 1 section, which is meant to commence a new standard of care for structural fire protection. And it's actually the first time that fire resistance has ever been acknowledged in this standard. The default option is for the designer to follow the standard fire resistance design provisions in the applicable building code without exception or extrapolation. As an alternative, the designer may adopt a structural fire engineering approach as constituted in the new Appendix E section of ASCE 716. The new Appendix E section provides overall requirements, skeletal requirements, for structural fire engineering designs. The appendix is broken down into 6 sections, and they each have commentaries. But from my perspective, the most important sections pertain to the required analysis scope and the performance expectations of the structure. In terms of the scope, Appendix E defines a specific design methodology. This includes evaluation of fuel loads, as I mentioned, in fire scenarios, which then produce thermal boundary conditions on the structure. From this step, a structural engineer becomes integral to determine the adequacy of, or perhaps explicitly simulate, the response of the structural system. Section E.4 of ASCE 7 divides performance objectives into those that are mandatory and those that are discretionary per the jurisdiction. Mandatory objectives, as the name states, must be satisfied in all cases, and they pertain to the intended functionality of occupant egress features. Specifically, the structural system shall allow occupants to travel safely, to exit safely from the building entirely to a public way. So this differs from how the building code treats evacuation, because the building code does not regulate the evacuation time. It only regulates how far you need to travel on a given floor to reach the stairwell. So the building code treats you as that you are equally as safe on the 100th floor landing of a stairwell than you are outside the building in the roadway. There's an implicit assumption that the structure will be adequate there. We require here that you explicitly demonstrate that everyone can get out of the building. I mentioned that all other performance objectives are discretionary, and satisfaction of these additional objectives may be deemed necessary by the project stakeholders, including the building authority. In all cases, discretionary performance objectives should be agreed upon at the outset of the project by all stakeholders, and this agreement should be memorialized in what's referred to as a design brief document. In fact, composition of a design brief should always be the first step of a structural fire engineering design before any pencils to paper in terms of calculations. For information on composing a design brief, the Society of Fire Protection Engineers publishes a guide, one that is directed towards designers and one that's directed towards reviewers, perhaps a third-party reviewer. Section E.5 provides requirements on the evaluation of fire exposure to a given structure. Notably, this section upholds the true intent of structural fire protection, which is meant to serve as a critical backup safety system in cases where active systems, such as sprinklers, are rendered inoperative or ineffective. So a sprinkler system could be Water may not reach the piping. It could be inadvertently shut off. There could be poor maintenance. If water makes it to the fire, it may not be enough water to put out the fire. Once the thermal boundary conditions from a structural design fire is a subset of design fires because they're always uncontrolled. But once you determine the structural design fire, Section E.5 provides requirements for evaluating the thermal response of the structure using heat transfer calculations. And once that thermal response is determined, it can be evaluated as structural temperature histories. So the structure of a given component at a given time. Section E.6 provides structural analysis requirements and states that the designer must consider the heated portions of the structure as well as those unheated portions of the structure that provide thermal restraint, as we talked about. Also, unlike design for ambient loads, you're allowed to rely upon load redistribution as well as alternative sources of load carrying capacity. When conducting a structural analysis, Section E.6 requires the designer to use the structural load combination for extraordinary events, which is appropriate for an uncontrolled fire. So that would be the 1.2 dead load plus 1.5 live plus 0.2 snow, and the A is the load effect resulting from the extraordinary event. In addition to Appendix E, our Fire Protection Committee, which is currently chaired by Dr. Jose Terrero, developed the first of its kind manual of practice. This 250-page manual serves as a companion guide to Appendix E. Whereas Appendix E specifies what needs to be considered and performed, again, there's skeletal requirements, the manual provides another layer of depth with best practices and recommendations on how you can execute these analyses. The manual of practice is broken down into 10 chapters. Notably, Chapter 3 provides detailed guidance on handling discretionary performance objectives, so a lot of practical guidance there. Also of note, Chapter 10 provides structural limit state acceptance criteria for fire effects. So in light of what we discussed, let's revisit that Chapter 1 section in ASCE 716. As previously mentioned, this section clearly defines and effectively bifurcates the two design options for structural fire protection. So if you're going to proceed with either option, you need to stay in that lane from beginning to end. There's no intermingling of incompatible metrics from each. ASCE 7 and the new manual practice reinforce, as I mentioned, that it's improper to marry aspects of standard fire resistance design and structural fire engineering. The metric of fire resistance is an artifact of the furnace test and its acceptance criteria, and there's no correlation to actual performance. So if you're performing structural fire engineering and you're using the metric of fire resistance, that is wrong. Since standard fire resistance design does not evaluate the capacity of the structural system, the safety margin is indeterminate. Conversely, a structural fire engineering design is conducted in the same spirit as a conventional structural engineering design that you're all familiar with, which provides an explicit understanding of the intrinsic safety provided. With the expected proliferation of structural fire engineering in the United States comes new opportunities for us as structural engineers. I can't stress this enough. Since standard fire resistance design is fully tethered to an empirical indexing system that has remained relatively unchanged for a century, designers are only able to influence a small number of design variables, primarily the level of protective insulation that designate the structural system components based on furnace testing. Since structural fire engineering designs explicitly calculate intrinsic safety margins, the designer is able to influence a greater number of design variables in order to either decrease demand and/or increase capacity to suit their purpose and performance expectation. Even more important than design freedom for stakeholders and economy of construction, structural fire engineering provides a high level of design transparency and basically explicit understanding of intrinsic safety, which results in a consistent evaluation of structures in this respect. So now that we've gone over the foundation by which structural fire engineering will allow us as structural engineers to influence structural fire protection, I'd like to walk you through from beginning to end an exemplar structural fire engineering design to give you an idea of the type of analyses that are involved, and also to give you confidence and empower you that as structural engineers, you're 90% there. There's just that little bit of 10% learning that if you are motivated, you can become someone that works in this field. The design I'm going to walk you through is from the recent project that's meant to showcase structural fire engineering as an emerging technology in the AEC sector, specifically in response to the advancements in standardization that I mentioned that have been made in recent years. The Charles Pankow Foundation and SEI have banded together to fund and administer 4 trial designs that are meant to accelerate the adoption of structural fire engineering in the United States. The Charles Pankow Foundation, along with other organizations, have generously funded about $250,000 for this project. The exemplar designs examine 4 previously and anonymatized buildings with regional representation: East, West, South, Midwest. Aside from serving as the principal investigator for the project overall, I also led the technical work for one of the 4 trial designs, which I'll focus on in this section. Overall, we're hopeful that these designs will showcase this technology as well as alleviate any concern for implementation and practice. And more importantly, we want to empower structural engineers to practice this. That is very important. And one thing that will be helpful is our report, which is currently being processed by ASCE Publications, will be free to the public in the coming months. I would estimate about 3 months. You'll be able to get everything. We want full transparency. The teams consist of representatives from 4 structural engineering firms, as well as academic advisors, basically playing the part of a building authority from 4 universities with significant expertise in this area. And we really cultivated a collegial atmosphere on this project. You know, we weren't looking at each other as competitors. We were looking at each other as compatriots to benefit and advance our industry for the betterment of all, because the rising tide will lift all boats. Representing the eastern region of the United States, our team analyzed a typical steel frame office building that was built in the early 2000s. The building has 6 stories and approximately 24,000 square feet per floor. This building prescriptively requires all steel framing, including the roof, to have a 1-hour fire resistance. The other teams also analyzed existing structures such as a hospital and a high-rise building. Although I won't cover these other structural fire engineering designs, I certainly welcome and encourage you to read the public report so you can also learn about these other really cool designs. So how did we conduct our design? So we wanted to look at two things. First, we wanted to look post-mortem at the structure that's actually built. So in this case, it's the original structural design for ambient loads only, and the fire protection was blanketed across the entire structure. The structural design primarily and customarily relies on one-way action of the slab, secondary members to girders, girders to columns. So one-way action. Also, the protective insulation or fireproofing, spray fireproofing was applied in the field. In this nominal case, represents how the majority of steel structures, in my experience, are designed and protected in the United States. But then we took another look at it from a structural fire engineering perspective, and we came up with an enhanced case. Here, our structural design has not only accounted for ambient loads, but also fire effects. We conducted our structural analysis to facilitate the safe deflection of floors, because floors are, even in a furnace test, they're inevitably going to undergo a large deflection. So we want to make sure that as it deflects inevitably, it's going to be safe and stable. And as you'll notice on the right side, we're not protecting all the members. We're only protecting the members that we need. And we wanted to position our design not to be a code-prescribed prescription of fireproofing, but a performance specification for fire protection that would facilitate the off-site application of protective coatings. So if designed properly, this enhanced case would allow for floors to become stronger and stronger as they deflect under elevated temperatures. This mechanism is referred to as compressive tensile membrane action. This would be analogous, as shown on the right side, to pushing down on the center hub of a horizontally oriented bicycle wheel, in which the system stabilizes itself as a tensile membrane with forces in the spokes that are in tension, equilibrating with compressive membrane forces along the periphery of the rim. In this case, the spokes are analogous to enhanced reinforcement in the slab, so upgrading the welded wire fabric that's already there for service. And the rim is analogous to the periphery concrete, which conveniently, as structural engineers, we always over-design because we want a tensile failure mode. However, all other floor members and columns would require protective insulation in order to support the edges of our bicycle wheel, keep it elevated in space. And also, we don't want the slab undergoing a crack geometry that would become unstable. So we need to control the deflection of those periphery members. But we can allow for some deflection. It just is engineered, as I'll get into. So for the fuel load, we first calculated a nominal design value that accounts for all of our relevant risk reduction factors per the Eurocode 1 method. Based on this, we calculated what we termed to be our design fuel load of 374 megajoules per meter squared, so the embryo of potential energy. However, in order to demonstrate a robust and reliable design, we opted to primarily consider an elevated, quote-unquote, above the design fuel load of 613 megajoules per meter squared, in which we neglect all risk reduction factors per the Eurocode. In addition to the baseline level of fuel load, we also considered two further elevated fuel load levels to help us understand the overall fragility of the structure. First, the quote-unquote ultra design fuel load, which is 912 megajoules per meter squared, reflects a 98 fractile nominal fuel load instead of the recommended 95% fractile. Lastly, we arbitrarily increased the quote-unquote design fuel load times 3 to arrive at a nearly inconceivable fuel load for our given occupancy. Enclosure fires are primarily governed by the fuel load, the compartment geometry, and the ventilation openings. Since the final arrangement of interior walls may not be known initially or may change over time due to remodeling, we analyzed a number of conceivable compartment geometries and ventilation levels. In general, lower ventilation tends to extend the duration of the fire, but can also reduce its peak intensity by limiting the oxygen available to combustion. On the other hand, higher ventilation conditions can increase the fire's intensity, but can also allow for hot gases to escape, thus reducing temperatures at the same time. Shown here are 2 scenarios where the fire causes complete window breakage, each representing what we characterize as a highly ventilated condition. Representing low ventilation conditions are shown here. And these are 2 other scenarios in which the facade glazing does not break at all, because those are kind of randomized events. For these cases, the ventilation is only provided from modest openings within the interior walls towards the core of the building, which allow hot gases to exit the fire zone to other areas of the floor plan. If the ventilation were reduced any further than this, we may eventually run out of oxygen and it would self-extinguish. So we felt that these 6 fire scenarios, and again, there's 2 that are sort of moderate ventilation that we also looked at, we consider these to effectively bound the problem for this given building. So considering the 6 scenarios with elevated fuel load levels, we calculated 11 structural design fires and their time temperature histories that we need to consider. Also shown here, there's different combinations of fuel load, compartment geometry, and ventilation, and the fires range in peak temperature from about 900 centigrade to 1300 centigrade, and durations that last between about a half an hour and 2 hours, depending upon the specific conditions that are present. So what we found is that the nominal design, which relies on one-way action with no structural upgrades, becomes fragile at a relatively modest fuel load after a relatively modest level of fire exposure. And we realized that the structure, in order to be reliable to our liking, really needs some enhancements. So these are the type of enhancements, targeted enhancements, and we try to keep them as modest as possible, that we implemented based upon our understanding of the fragility of the nominal structural design, even though all the members were fireproof. First, we increased the mesh density modestly. We also lowered the mesh within the slab to a level by which it still serves its serviceability crack prevention requirements, but increases the effective lever arm of the mesh acting as the floor undergoes large deflection. Also, at the slab edges of the building, we detailed proper anchorage of the mesh passing at a low enough elevation along the periphery shear studs to provide a sufficient level of anchorage to make sure that as the floor deflects, the slab does not fall off the supports. Also, the primary connections, the girder to column connections, we provided some enhancements. I would say the one shown at the top right is the most, the biggest level of enhancement that we had to do, which is add a bolt and increase the bolt hole edge distance very, very modestly. I think it was about a 1/4 inch. Also, one thing that we looked at is as floors expand, at the edge of the building, they're pushing out on the column. And this can lead to some failure modes of that column. So we made some targeted enhancements to the exterior columns, notably shown at the bottom right, is we opted to have hollow steel sections instead of an I shape there in order to provide better stability of those periphery columns. And also, as I mentioned, it's only the primary members that are protected with insulation, and they have a performance specification. So this graph basically shows the demand in the blue line, which stays constant, which is the extraordinary load combination. In the dotted lines is the beam capacity, or the unprotected secondary members capacity, which, as you can see, as it heats up, goes down to pretty much nothing, as well as the slab's capacity, which, as you can see, as it deflects, as the slab deflects, it becomes stronger and stronger. And what's shown in the yellow line is the addition of both the beam and slab capacity at any given point in time in the fire, throughout the heating phase and cooling phase. So this is our DCR comparison as a history. We also did finite element modeling to make sure that the system is behaving the way that we anticipate. And this is a snapshot of the floor system, a single bay, after different points in the fire exposure. And as you can see, as the fire heats the structure, we're getting that tensile zone in the middle and that compression ring as we would expect. And then as the system is cooled, you can see that it's going back to its original one-way action as designed for ambient. To provide some validation and confidence in our calculations and simulations, there is a fire test that was conducted in Europe that has pretty similar conditions. They have a larger span and a thinner slab, but very similar mesh density and strength that we designed, and also it's similar fire intensity. And you can see at the top right, that's pretty much what our welded wire mesh would look like, because they had almost the exact same sizing of the mesh that we chose. And you can see in the bottom right corner that the secondary members undergo lateral torsional buckling, and they become pretty much ineffective at resisting load. But the system as a whole is robust under fire, and there's no collapse. We also need to look at the fire effects on connections. And the fire effects on connections will vary based upon what connection and what location of the building. So first we looked at locations shown in the 4 blue dots, and we plotted the force history on each of these connections throughout the heating phase, which would be compressive, and the cooling phase, which would be thermal contraction and pulling in on the connections. And as you can see, there's symmetry here because there's symmetry of restraint. However, if you look at an edge bay, there's only symmetry in 2 directions. So there's a sort of bifurcation of the force histories at the connections depending on where you are. And if we look at a corner column, a corner bay, there's no symmetry in either direction in terms of the restraint conditions. So the force histories on the connections vary depending on what corners you're looking at. So we accounted for all restraint conditions that may be present. And aside from cost considerations that we'll get to, the Design 3 allowed us to design a structural system that's able to withstand a myriad of increasingly intense fire exposures. So unlike the nominal design, the full integration of a structural engineer into this process provides a design that is far superior from a performance perspective. Specifically, under increasing levels of fuel load from conceivable to pretty much inconceivable, the structure performs admirably. Even considering the nearly inconceivable ventilation and fuel load conditions for this occupancy, the structure still allows for full evacuation of occupants with extra time to spare for firefighting operations. This provides a truly reliable backstop for a design which meets the minimum mandatory performance objectives of ASCE 7. But for more expected or conceivable conditions, it's providing optimal performance. There's no collapse under full fire burnout. So overall, the variety of conditions in which the structure performs adequately compared to the nominal case demonstrates the reliability and robustness of our enhanced design, which was not possible with the nominal case. So shown here is our applied protection scheme for a typical floor. The members shown in blue are designated to receive off-site applied intumescent coating. So this is where the protective coating can be applied with a high level of quality under controlled factory conditions. And we have a performance specification for this coating based upon our structural limit states. So we basically specified the coating under a given fire hazard to limit the deflection of periphery members enough to uphold our slab yield line assumptions. So effectively, this design approach shifts reliance from the insulation itself to the intrinsic strength of the structure to endure the fire adequately. So our final report will be freely available, as I mentioned, and if you examine the cover, you'll notice that we omitted any imagery of fire itself, which many books of this type, primarily in Europe, usually have. And we did this intentionally to prevent you from thinking that you can't do this. Okay, what we show here are essentially force diagrams under different points in the fire. We really want structural engineers to be able to relate to this technology. So fire is not some exotic thing that is beyond your expertise per se. You know, you may need assistance from a fire consultant, but you already design structures in a lot of cases for thermal expansion, but now we're just talking about a lot more thermal expansion and contraction. So the last part of this talk, and it seems like we're making good time, because I want to leave time for questions, is how can this awareness and proliferation of structural engineering impact our industry for the better? That's what I'm going to go through in this section. So I've covered the findings of our project. Now let's discuss how the AEC industry can benefit from this. As a start, I've shown here the annual report from the Charles Pankow Foundation. And here the foundation reaffirms their belief that structural fire engineering will be a game changer for the United States. And being an organization that's focused on promising technologies for the AEC sector, their strong endorsement of this method is very promising, and we're very thankful for that. So as structural fire engineering gains traction in the United States, how can it affect the economy of construction? First, let's start by examining conventional structural engineering that we're all familiar with. Structural engineers traditionally optimize their designs for steel tonnage and erection costs, above all. This is certainly prudent, considering that steel tonnage accounts for approximately 55% of the total cost of a steel structure. However, structural engineers may not always be aware that applied fireproofing actually accounts for approximately 20% of the total cost of a steel structure, which can actually exceed the cost of the structural core of the building, which would account for about 15%. And again, this may vary. So I asked the question, is optimizing a structure for steel tonnage and then arbitrarily blanketing the structure with fireproofing, is that truly optimization? From my perspective, optimization of a slice of the pie, even though it's a big slice, is truly not optimization of the pie overall. Plus, as we've covered, such an approach does not result in any real understanding of how the structure actually behaves under uncontrolled fire. So, from my perspective, the lack of synergy between structural engineering design and structural fire protection, which has gone on for a century, can result in buildings that are less resilient and cost more than they need to. Think about the enhancement of the mesh. That has benefits beyond just fire. If you're designing floors to become tensile membranes and you have a bomb blast that takes out a column, you could synergize those designs and you have mutually benefit aspects, but chances are that a structural fire engineered building is going to be more resilient to that, even if not specifically designed. This is not to mention that structural fire protection often represents a major roadblock to design innovations because you're mating a 100-year-old technology with modern construction. Not a good combination in all cases. How about we zoom out even further and consider the total cost of the core and shell of a building? In this case, the accepted construction inefficiencies become even more pronounced. For reference, the cost of the protected steel structure only accounts for about 12% of the entire core shell cost, which actually, that can be kind of humbling to us as structural engineers. Most of the overall cost is attributed to the service and cladding installations that account for about 60% of the building cost. However, it's sobering to realize that all of these installations cannot commence on a project usually until the fireproofing is sprayed, cured, and perhaps inspected. And I've been on projects where inspections of fireproofing are definitely on the critical path. Not to mention, this would be under ideal temperature and humidity conditions, which can delay fireproofing if they're not ideal. As a result, fireproofing, which only accounts for 2% of the entire big picture, can actually have a very amplified effect on the entire construction schedule and economics. So in summary, our analyses on the Charles Pankow project demonstrate that the adoption of structural fire engineering can significantly enhance many aspects of building construction, and these benefits are most pronounced when structural fire engineering is harnessed with a performance-specified and perhaps off-site applied coating scheme. And this is because such a scheme can relieve major pinch points in a typical construction process. For our individual building, we estimate that this approach for the 6-story building would reduce the construction time about 5 to 6 weeks. And granted, this reduction in construction time would conceivably be greater for taller and larger buildings or buildings with more speculation. Overall, the financial benefits of injecting structural engineers into the archaic realm of structural fire protection can be modest or enormous depending on the project. Generally, this depends on the specific building under consideration and its circumstances. As I mentioned, its level of speculation, such as time to rent, its construction complexity, such as tight access conditions. Also, the proliferation of structural fire engineering in the U.S. will lead to more intrinsically safe and efficient structures. So we can look ourselves in the mirror and not only be adding value, but benefiting society at the same time. This proliferation should provide many opportunities for structural engineers to not only serve as integral participants in the design of structural fire protection, but as I mentioned, can add profound value. I'm a true believer of this. I'm a junkie on the subject. And from my perspective, this proliferation will change the way that project stakeholders view the optimization of a building. Thank you kindly for your attention, and I'm happy to entertain questions.
Thank you, Kevin. We don't have any questions at this moment in the chat box. If you have any questions, put them in. Actually, one just came in. Does structural fire protection vary between steel and concrete structures? Is there one system better or provide advantages?
I wouldn't say one's better or the other. Again, it depends on a lot of circumstantial factors. But just to go to the basics, steel is typically protected with applied insulation, whether it be fireproofing, which is acting as just an insulator, or intumescent, which is a paint or epoxy that expands and kind of forms a char layer and also has an endothermic reaction to it. Concrete, we're primarily providing an adequate amount of concrete cover to insulate steel reinforcement. And again, one thing to think about that steel mesh that I talked about. In fire resistance qualification, the mesh is kind of inconsequential. But when harnessed in a structural engineered method, it's actually a very highly insulated structural component. Think about it. It's up in the slab. It's going to stay very cool. That's something we can harness to make it work. So they both, and timber has its own ways of providing fire resistance, but again, structural fire engineering provides the opportunity to be innovative in the way we protect each of those. And structural fire engineering and the standards by which have been developed, they're not discriminatory to materials as long as there's sufficient first principle knowledge for each one. Thanks for that.
Another one coming in. What SFE changes are in the works for the upcoming ASCE 7 in 2022?
That's a great question. We're currently subcommitting, we're balloting within our general requirements subcommittee at the moment. Some updates mostly to that Chapter 1 section and Appendix E. It's mostly to clarify our original intent, make things a little more explicit in terms of the intent. For example, making it very, very clear that if you're doing structural fire engineering and you're using metric of fire resistance, that is unacceptable. Also unacceptable. If your structural design fires are controlled by sprinklers in your design, or controlled by any assumption that firefighters will be able to manually intervene and control the fire, that's unacceptable as well. We're making sure that that is clear in order to have a high level of quality and a high standard of care as we go about this. So thank you for that.
And one other, intumescent paint. Is the cost as prohibitive as it used to be, or is it more in line with spray-on fireproofing?
Sorry, could you say that one more time about intumescent paint?
Intumescent paint, just its cost prohibitiveness. It used to be prohibitive based on its cost. Has it come down so that it's more reasonable compared to a spray fireproofing?
Sure. There's different types of each, so I don't want to make a generalization, but intumescent predominantly on a material basis is more expensive than traditional fireproofing. However, structural fire engineering allows for putting everything on the table in terms of cost: material, impact on construction schedule, aesthetics, carbon footprint, site safety, and also the structural enhancements you would need to make it work. And allows you to compare those two in a very sober way. So to say structural fire engineering will always deliver a least expensive solution is not right. it has the opportunity in a lot of cases to do so, even with a more costly protective material that's strategically placed and performance specified. And also, since it's performance specified, you're only putting it on there to control the deflection of the periphery members in our case to a certain extent to uphold your yield line theory. There's a lot of allowance there for deflection. So you may not need as much of it even on those strategically protected members. So again, what's the competition here? You're competing against a 100-year-old technology, but your engineering, structural engineers, can compete against that, I believe.
And we have another question. Are the structural fire engineering methodologies in ASCE 7 Appendix E recognized by the IBC?
I appreciate that. I'm actually chairing a working group. I'm a member of the ICC FCAT committee, Fire Code Action Committee. We're about a 16-member committee, primarily building officials, but had the opportunity to be a voting member of this. I am currently championing with others and with other letters of endorsement full integration of this into Chapter 7 of the IBC to explicitly recognize ASCE 7 as a method by which to apply to provide structural fire protection. Currently, you would have to use the alternative means and methods clause within the IBC to employ, and also within Chapter 7 currently there's kind of like an open-ended alternative methods that could be elicited or alluded to. There's no barrier to entry at the moment except the comfort of the building authority. So this method is elective per the building authority and their ability to review it and gather third-party peer reviews. But we want this really to be treated no differently than performance-based seismic design or performance-based wind design. And we're trying our best to follow in the good footsteps of those two disciplines.
Okay, here's another one. Does SFE increase the likelihood of significant damage to less than design load fire with a rapid response from the fire department due to the fact that there are some of the members are completely unprotected?
So I gather that question is basically, since you have unprotected members, does it make the system more fragile to failure? Absolutely not. If you have a structural fire engineered system, it's intrinsically safer to elevated temperatures and cooling after fire.
Okay, and one last one. On what type of project or what type of jobs are these services typically enlisted? It would seem the cost of these services could be prohibitive if it can't be established in advance that net savings would be realized. Similar wind studies versus ASCE 7 wind loading.
Well, at the moment, I would characterize as it takes a special client and a special building authority and a special vision to employ this. However, it is in its infancy, but there have been projects, I won't go into specifics, but very iconic projects that have come online recently that benefited dramatically, and the costs associated with employing the structural engineer beyond what is typically their remit became inconsequential compared to the value that was injected into the project.
One other came in. How do we define restraint of a member for fire rating? The IBC is generally vague on stating that restraint classification is in accordance to the ASTM E119 or the UL 263. What other resources would you direct us to?
Sure. So you're talking about standard fire resistance design, and I actually co-authored with 8 other co-authors in Fire Materials Journal recently that is entitled Rectification of Restrained versus Unrestrained, which talks about this. Also, there's a Structure magazine article entitled Restrained versus Unrestrained, where I serve with 2 other co-authors, that talks about this issue. From my perspective, the definition of restrained does not exist. It's a paradox, and it's something that we need to reform. But, you know, based upon the topic of this lecture, I don't want to sort of get bogged down in that, because that's pretty much an artifact of standard fire resistance design. It has absolutely no bearing on structural fire engineering.
Sorry, it looks like we have no more questions. Thank you, Kevin. That was an excellent presentation.
Thank you so much.
And I would like to thank SEI, in particular Kevin and Donald and Evan, for putting together this presentation. Also, keep your eye on your email inboxes for some events planned by the Education Committee and the Younger Member Group in the next month or 2. Also, our next general meeting will be September 17th, and it will be a presentation provided by our Still Committee. So everybody, thank again for everybody for participating and sitting in on this webinar, and stay safe out there.